Hello and welcome to a screencast about properties of quadratic functions. All right, here's a blast from the past, I'm guessing from most of you guys, the quadratic formula. All right, so the function q of x equals ax squared plus bx plus c represents an infinite family of quadratic functions. And you notice this is a function, where each member of the family depends on the three parameters a, b, and c. Okay, so we're going to be dealing a lot with parameters this semester, so get used to having some variables in there, or some parameters in there along with your variables. Okay, so now we're changing from a function to an equation. So those are two very similar but yet different ideas, so make sure that you're always paying attention to which one we're asking for, which one we're dealing with. So let a, b, and c be real numbers with a not 0, because if a were 0, then that would wipe out this first term here, which would make it linear, not quadratic. The equation ax squared plus bx plus c equals 0, so we're dealing with the form we had up here, but now we're setting it equal to 0, which makes it equation. So this equation can have 0, 1, or 2 real solutions. These real solutions are given by the quadratic formula, this big old monstrosity here, provided that b squared minus 4ac is greater than or equal to 0. Okay, so let's do an example, because that's always important. So here I ask for the solutions to the quadratic equation, and again, you notice I use the word equation here because there's an equal sign, and there's numbers and stuff on both sides, not f of x or something. So we have 3x squared minus 4x equals 6. Okay, so looking up here, first thing I need to do is I need to set this equation equal to 0. So I'm going to scoot that 6 over. So I have 3x squared minus 4x minus 6 equals 0. Okay, now I want to pick off my a, b, and c. So those are my parameters. So a is 3, the coefficient of x squared. B is negative 4. You notice there's a negative in here, the coefficient of the x. And c is your constant term, negative 6. All right, let's plug those into our quadratic formula. So the opposite of b, so my b was already negative 4, so it's going to become positive 4, plus or minus the square root of b squared, you notice I'm putting this in parentheses, negative 4 squared, minus 4 times a, which is 3, times c, which is negative 6, all divided by 2 times a, which is 3. There's a nifty song that goes along with this too, if you ever want to learn that, but I'm not a singer, so you're out of luck. All right, 4 plus or minus the square root of, oh boy, okay, so negative 4 squared is 16, and then we've got minus 4 times 3 is 12, times 6, I believe is 72. It's negative, and then there's a negative here as well, so that ends up giving us plus 72. Hopefully my mental math is correct. And then finally I can add my 16 and 72 together, so this gives me 4 plus or minus the square root of, I believe that's 88, all over 6. Okay, you can break this down some more too if you really care, but that's going to give us then my 2 solutions. Okie dokie. Important points on a quadratic function. So why would I want to solve this? I mean, yeah, it's fun, right? Moving math around, doing math, it's always fun. But why is it actually useful? Okay, so I know our last answers were kind of ugly. So let's pretend like we were solving in a quadratic equation and we ended up with the solutions of, let's say like x equals 3 and x equals negative 1, for example. Okay. So because a quadratic equation is set equal to 0, these are actually considered my x-intercepts. So what they can do then is, because there are x-intercepts, if you think backwards, that must mean that we can make factors out of these. So that must mean that x minus 3 and x plus 1 would be how we could factor the quadratic the quadratic function that this quadratic equation came from, if that makes any sense at all. Okay, so that's where this can actually be helpful, because it can help you find x-intercepts and it can help you write things as factors. So in general, I wrote this out here from the book. So in general, we know the x-intercepts of a quadratic function, also called the zeros, which is why then they pop out of your quadratic equation, are, let's see, r comma 0 and s comma 0. And we know x-intercepts have y values of 0, so that makes sense. It follows that we can write the quadratic function in the form q of x equals a times x minus r times x minus s. Okay, so I just assumed for this one my a was 1, but yeah, that's okay. All right, great. Every quadratic also has a y-intercept and a vertex. Oopsie, we don't want to do that. So let's say we've got, I don't know, how about a quadratic function looks like that, for example. So we've got a y-intercept here, obviously where it crosses the x or the y-axis at. So this is where x is equal to 0. So if you think back to our form that we had earlier, the ax squared plus bx plus c, if we throw in x equals zeros everywhere, this then gives us the value 0 comma c, right? Because these first two terms wipe out. For the vertex, however, so the vertex in this particular case would be the lowest point on the parabola. It's also where you can kind of fold this guy in half. I'm not even going to try. We'll get to the next screen of where that actually comes from. I just wanted to draw that out. So this would be your vertex. So in this case, it's the lowest point on the parabola. But let's say your parabola goes the other direction. How about something like that? It's kind of sad, but that's okay. So again, we've got our y-intercept here. And then this time our vertex would be somewhere in here. So that would actually be the highest point on your graph. Okay, so now for the official definition here of our vertex. So the quadratic function y equals q of x equals ax squared plus bx plus c. Hopefully you're getting the hang of that one. Has a vertex at the point. Okay, brace yourselves. The x value of this vertex is negative b over 2a. Okay, kind of sort of looks like the beginning part of the quadratic formula, right? If you were to ignore the square root stuff. Then the second part here, what this is saying is whatever we get for that x value, we are going to plug it back into our function into q, and that will give us our y value. Okay. All right, when a is greater than 0, the vertex is the lowest point. Okay, so the lowest point, that would be the parabola that had it at the bottom. So this would be this type of parabola. So this would be a is greater than 0. Well, if a is less than 0, the vertex is the highest point. So the highest point one, I think I actually had it on the other side, but that's okay, would be this one. So this is a is less than 0. Okay, so there's our vertex. Now, another interesting part here is we've got symmetry. So Q is symmetric around the vertical line. Okay, so let me go ahead and do some more drawing here. So there is a vertical line that's going to go through that vertex. So obviously the vertical line has to have the same value as the x coordinate of your vertex. Okay, that makes sense. Same thing over here. This would be our line of symmetry. Whew, that's a really badly drawn parabola. I'm sorry. But what's supposed to happen then is if you were to look on either side of this line of symmetry then, those 2 points would have the same y value. Okay, the x values would obviously be different, but the y values would be the same. Same thing down here. Yeah, this one's really bad. Let's look at this other one. So here, if I were to look at my x-intercepts, those are going to be symmetric over that vertical line. Okay. All right. Hope this video helps and have a great day.